Hi everyone, my name is Gary Ang. I'm the founder of NumberSkill Learning Centre. Okay, and today we're going to cover this one very interesting shortcut method to do partial fractions for Sec 3 A Math. Alright, it's called a cover-up rule. Now this is more like a shortcut than a particular method. A shortcut in the sense that it helps you get your answer a bit faster than everyone else. So it is one of the most interesting method to solve it, and the funny thing is that not everybody will get to learn this in their school. So come on, let's try. Okay, so what is this thing called cover-up rule? Well, the idea behind cover-up rule is that we can actually solve this partial fraction questions rather quickly. Maybe, just like a magic show, I should show you the magic trick first, right? And then you decide for yourself whether, hey, you know, is it like quite interesting? Then we talk about the logic behind the magic, okay? So let me just copy this question at the side. Okay, so it's x over x minus 1, x minus 2. So of course, in partial fractions, the whole idea or the whole mission, right, is to split this up into two smaller fractions, right? And usually this is how we visualize it. So we're going to find A, and then we're going to find B. Okay, sorry, pardon my handwriting, okay? Alright, here we go. Now how we do that is of course the normal method, I suppose you already learned in school, so it's the same kind of multiply throughout and then flatten it. But then again, there are different methods to do the same job, which is to find A, find B. Now the cover-up rule works a bit this way, alright? So we say that, oh, you know what, to find A, I will substitute x equals to 1 over here. Alright, so I substitute x equal to 1, and guess what? I'm going to get 1 over 1 minus 2, and that will be minus 1. That's A. Full stop. Done. We're done. That's A. Then go like, wait, sure. What just happened here? Okay. So like I said, the thing, the math that I'm actually doing right now is I substituted A over to the left hand side. Now it is substituted x equal to 1 into the left hand side. Now of course it is not difficult to understand what is actually happening because, well, x equal to 1, that's how I get this 1. That makes a lot of sense. X equals to 1, and that's how I get 1 minus 2. Here we go, right? The 1 minus 2. Now, but then there lies the problem. When x equal to 1 here, you have a 0. Alright, and 0, obviously, you can't divide by 0, so that's a no-no, right? So that's why we cover this up. So it's just cover-up rule. Alright, but you can see that the effect of how the thing actually works if you know how to use it properly, right? You got A as minus 1, hey, pretty quickly, right? Now then the next thing you ask is actually how do you know you substitute one number, right? Okay, let's do B. Okay, so to find B, right, what I will do is I will put the I'll look at the denominator, which is x minus 2. So x minus 2, then I'll substitute x equals to 2. And you guess it, you substitute to the left hand side. So as you can probably imagine that there will be a 0 again. That's where it's called cover-up rule. So B is literally 2 over 2 minus 1, which answer is 2. We're done. Okay? So of course, without the commentary, I mean, without me explaining what I'm doing here, well, getting to these two numbers are actually quite straightforward and fast. And that is the magic trick of cover-up rule. Now, of course, you might go like, oh, okay, that sounds quite magical. Now, of course, when you learn a shortcut, you want to learn it properly. Learn it inside out, learn it well, so that you know what's actually going on, what you're actually doing, what is legit, what is not legit. Okay, and the reason is because otherwise you will be following a set of instructions that you don't know what is actually happening. Now that can be quite dangerous, especially when it comes to more complicated questions. Okay, so now let's dig in to try to figure out how does this work. Okay, so the cover-up rule, like I said, is just a shortcut. Okay, so if you don't know it, it doesn't mean that you can't score well for this particular topic. So and you'll be surprised that the working mechanism behind cover-up rule is actually the same as how you have done it normally. Okay, let's talk about the normally, right? What do you mean normally? Normally, what do we do? So like I said, usually, okay, we split it up this way, right? That's usually step 1 of the cover-up rule, right? We split up into the individual smaller fractions. And then what we do is we try to make all the fractions go away, disappear. So this is what we call multiply throughout. I like to call it flatten, right? Flattening it. So because it's double decker, so we make it flatter, right? So how do we do that, right? We multiply throughout by the common denominator, which is in this case x minus 1, x minus 2. So you multiply to the left and you multiply to the right. Yeah. Okay, and of course, when you multiply this to the left, you are obviously going to be left with just x, right? If you multiply this whole thing to the this fraction, of course, this x minus 1 cancel away, and you'll be left with a times of a x minus 2, which is this thing over here, right? And if you multiply this product into this, right, the x minus 2 and x minus 2 will cancel away, and of course you'll be left with b times of x minus 1. So all in all, the whole idea of multiplying throughout is to flatten the equation into a single layer kind of thing, right? So instead of dealing with fractions, now we're dealing with an algebraic expression or equation like this. It turns out that to solve for a and b, well, we are quite hopeless here because after all, this is two unknowns in one equation. We can't really solve it in the way that we solve our algebra normally. So in this case, there was only one hope, right? To find A, find B, because after all, the left side is equal to the right side. So in order to find A, all right, we try to make B disappear. So this is a substitution method, right? So to make B disappear, I substitute x equal to 1, right? Because when you x equal to 1, when you put in x equal to 1, 1 minus 1 equals 0, so this thing is 0, gone. And of course, when you substitute x equal to 1, you have to substitute x equal to 1 everywhere, right? Because, I mean, x is 1, then this x is 1, that x is 1, every x must be 1. It cannot be this x is suddenly 2. So all the x become 1. So for a moment, let us just not do the number. I want to show you the magic, the logic behind the magic, right? And that is when x is 1, this thing disappears, okay? So we get a 0 at the back. Now, before I put in the x equal to 1 value into the rest of the x, right? I want you to see that the equation that we flattened earlier on now suddenly becomes something like this, which is okay, quite understandable, isn't it? Because when x equal to 1, this is 0, that's the whole idea, right? Then I can find a now. And of course, we divide across, you realize that a is actually equal to x over x minus 2, the printed in red kind of font there, right? This is in fact right here, isn't it? So in short, what we were doing here on the left side, right side, you can see that, let me use another color, okay? So red color, this, okay. So you can see that to find A, I literally just take this part here and I put in x equal to 1, which is what we get from here, because the B will be 0. Now, and why x equal to 1 is because that's the whole idea, isn't it? Because we look at the denominator of A, and that's x minus 1. So this x minus 1 turns out to be what B will be multiplied by when you multiply throughout. I know it sounds quite complicated, right? But if you look through the steps that we're doing right here, this is very easily understood, okay? It's very easily like, hey, this is exactly what I will be doing. Okay, and this is exactly what my teacher taught me in school. But what we did over here, okay, if you look at it side by side, like now, okay, what we did over here is literally the same thing, isn't it? I mean, we are going to put in x equal to 1. We're going to put in x equal to 1 here. And of course, we're going to end up with the same answer. But what happened on the right side is that we didn't show all these workings. So that's why I say it's really just a shortcut, okay? A shortcut, nothing too magical about it, now that you know what's actually going on behind the scene, okay? But of course, when I first learned this, I was like, hey, that's amazing, like, wow, so magical, how does it work? It's, like I said, it's almost like a magic trick, right? So it looks so magical and so unbelievable, until you know the secret behind it. You go like, actually, okay, quite easy to understand. Okay, so let's move on to talk about B. Okay, so if you understand that, we can proceed along to find B and discuss B. So when we talk about B, okay, if we want to find B, right, of course we will try to make A disappear. And to make A disappear, I have to substitute x equal to 2. So x equal to 2, of course, will be the the value that will make the denominator of b undefined, right? So again, we look at the denominator for ideas to understand what to think about the number to substitute in. All right, so x equals to 2. Okay, so x equals to 2 to substitute in to find b, because this will be gone. So imagine in your head that this is gone. Okay, so this is gone. So once this is gone, the b is actually x over x minus 1, which, if you look closely, is right here. Okay, maybe erase this and you can see it here. Okay, so which is of course when x is equal to 2, you're going to get 2 over 2 minus 1, which is, if you look over here, that's exactly what we're seeing, right? That's the vision that I was looking at when I was doing this earlier on to show you the carve-out rule. Okay, so all in all, the idea is that it is doing roughly the same thing as the normal way of doing it, which is multiply throughout and then find a, find b, substitute values to find a, find b. The only difference is that it looks a bit shorter. Okay, and to be seriously honest, yes, it can be faster, especially when the numbers are actually integers, whole numbers like this, and easy to calculate numbers. It may not be that much of a shortcut if the numbers are in fractions, right? Because if the numbers are in fractions, the calculation, well, may be more cumbersome, and you may end up still using calculator. So in that case, then you may want to just do the normal way in order to get your calculations right, instead of getting careless. So of course, when you're dealing with easy number, this is a great idea. In fact, I see it in my students' work when they use it to great effect, very fast. It makes it look like they are pro, actually. Okay, so and this is a skill set that will stick to you all the way beyond O-level. All right, so after O-levels, I'm sure many of us will continue studying. So wherever you go to, yeah, you will come across this. And if you know this carve-out rule, it'll be pretty much an advantage, because you can do your things a lot faster rather than a bit more kiddo, like, hey, hello, you're back to Sec 3 again. Okay, that kind of thing. Right, anyway, so of course, like all shortcuts in life, there's the pros and the cons, right? So we need to understand it a little bit, okay, a little bit deeper. All right, so of course, this is what we call case 1, which is rather simple, what we call distinct. Sorry, I'm using a wrong pen. Okay, distinct linear factors. So of course, is 1 by 1, right? Linear factor like this is distinct because they're different. So let's talk about the case 2 kind of application, right? What we call repeated linear factor. Repeated means you have more than 1. Usually in the syllabus, it's only square, so that means twice. Okay, so it won't be repeated 3 times. That is not in the syllabus. So anyway, these are what we call repeated factor. So repeated factor, as we understand, right, when we split up into the individual small fractions, there will be 1 for x minus 1, there will be 1 for x minus 2, and there will be 1 more for x minus 2 squared. So the whole idea of repeated linear factor, repeated, you have 2. Okay, of course, they can't be both the same, then what's the point? So there'll be one of it for x minus 2, the other one is x minus 2 squared. Now, of course, the normal way of doing is like what we discussed before, and probably you learned in class in school before, and that is multiply throughout, and then you end up here, you flatten the equation, alright, single deck here, and then of course you start doing substitution to find A, to find B, and to find C. Now, the carve-out rule will not work for B. Okay, in other words, the carve-out rule will only work for A and C. Maybe, again, I do a demonstration. Okay, so I'll just copy the same question here at the side. And you can see in action. Okay, so we have A over x minus 1. We have a B over x minus 2. And we have a C over x minus 2 squared. Now, knowing the carve-out rule allows me to find A. So I'll substitute x equal to 1. Okay, and A will be equal to 1 over 1 minus 2 squared. Of course, again, carve-out rule being carve-out rule, right? The term carve-out, we have carved out that offensive number called 0. Alright, in this case, I'm going to get 1 because the denominator is 1 minus 2, which is negative 1 square. You're going to get 1. Okay, you get the idea. That's it. We're done. A. Now, that I must be mindful because I learned shortcut. I must be aware of the dangers of the shortcut. Shortcut can only get me that far. It got me my A. It will help me with C, but not B. So let's go ahead and find C, okay? So I'm going to substitute in this case, x equals to 2. And I get my C, 2 over 2 minus 1, and that's 2. In fact, you don't even need to write this down, right? You can do a computation in your head. But I need to write out, otherwise you may not fully catch what I'm thinking, right? So I need to show you what I'm thinking in my head. Anyway, out of the 3 unknowns, you got 2. Okay, and these 2 unknowns by using cover rule. And to be honest, if you learn it well, you can actually do this in less than 1 minute. And usually when there are 3 unknowns, there are minimum 3 marks. You got 2 marks for finding the 2 unknowns in less than 1 minute. All that's left to do is to find B. Now, and to find B, the cover rule doesn't work. And when the cover rule doesn't work, well, we have to go back to the original way, which is the multiply throughout way. Okay, so when you multiply throughout, we're going to end up like this. Alright, here we go. So we end up with a C and then x minus 1. 这样. Okay, something like this. Okay, cool. Now, of course, we're back to square one. Right? Isn't this like the same as what my school teacher taught me? Well, to a certain extent, like I told you, we have no choice because to find B, the cover rule doesn't work. We have to come back to here. Alright, but the good news is that you already found A. Right? And you already know that A is 1. And nobody writes 1 in front of a fraction. Okay, so don't do that. Okay? We already found C. So that's the difference, you see. And to find, okay. Alright, and to find B, in this case, it is much easier because we can substitute any number. Like this is the last unknown, okay? It is the last unknown in the entire equation. So you can substitute any number you like, except you cannot substitute in 1 because if you substitute in 1, the B will be gone, B will be 0. If you substitute in 2, B will also be gone. Alright, so that's the whole idea of why cover rule doesn't work, because it'll be gone no matter what you sub in. So in this case, of course, we go back to our favorite number, substitute x equals to 0. So put in x equals to 0, we're going to end up with 0 minus 2, which is a minus 2 square 4, plus b minus 1 minus 2, and then plus 2 times of minus 1. And of course, figuring this out is not something very challenging, if you ask me, right? So we're going to have a 0 equals to 4 minus 2, which is 2, plus 2b. So b is equal to negative 1. Okay? So that's the carve-out rule way of doing. Now you can see that the carve-out rule allows you to find your A and C very quickly, which is the color, orange color set of workings. But of course, the carve-out rule doesn't work very well for B. In fact, it doesn't work at all. So you have to do the normal way, right? But that shortens your time because otherwise you have to find everything the normal way. Okay, now let's discuss why the carve-out rule doesn't work for B, but it works for A and C, right? And that's because if you try to do the multiply throughout, so for example, right, we're right here, right, after we split into the individual fractions, and we multiply throughout, we're going to end up here. Okay, I'm just going to use one of these lines to do our discussion. Okay, so over here, right, so we end up here. Now, you just think about it for a moment, okay? To find A, let's say I'm interested to find A, I need to get rid of B, and I need to get rid of C. And to get rid of B and C is not very difficult because, well, there's a x minus 1 here, there's a x minus 1 here. So the obvious choice is to let x be 1. When x is 1, well, this is gone, and I find A. Okay, and that is exactly what's happening here when x is 1. So I'll be able to find A, okay, which is how the carve-out rule works, and that's why it works for A. Okay, let's think about it again. Let's understand it this way. If I want to find C, okay, what do I do? Well, of course, if you look around, I need to get rid of A, I need to get rid of B, and A has got this x minus 2, B also has got this x minus 2, which means if I substitute in x as 2, this will be a 0, this will be a 0, I'll be able to find C. And again, that is exactly how I did it over here using the carve-out rule, right? So when x is 2, you'll be able to find C. Okay, so now I have explained why the carve-out rule actually works for A and C. Let's understand why the carve-out rule doesn't work for B. Okay, because, now let's think, guys. If I want to find B, and of course the mission is to get rid of C and to get rid of A, the way we did previously. The bad news is, in order to get rid of C, you need to put in x equals to 1. Yeah? and c will be 0. That's the whole idea. However, when you put x equal to 1, your b is also gone because there's a x minus 1 multiplied by b over here. So when you get rid of c, you effectively gotten rid of b at the same time. Okay, now it just got worse. Okay, now if I want to get rid of a, I put in x equals to 2. And at the same time, when I put x equal to 2, the b will be gone as well. So you can imagine now we have a problem, right? Because when you put in x equal to 1, I found my a, I put in x equal to 2, I found my c, and now if I put in x equal to 2, I will not be able to get b, because b will be gone at the same time. So this is the working mechanism behind, and this is also the reason I believe why this method is not so widely taught in school. Because it can get quite confusing, isn't it? Right? It can get quite confusing. Imagine a teacher trying to explain this to an entire class. Not everybody will be fully clear about what is actually going on. Wow, how come I substitute x equal to 2, it works for c, but it doesn't work for b and stuff like that. Alright, so of course this takes a bit of effort to try to understand. Okay, so much so that some teachers I heard of, right, when they teach carve-out rule, they told the students that, alright, it only works for linear factor, only this kind of fractions. So anything beyond this, like repeated factor, nah, it's not going to work. Okay, it's not entirely true, because it's going to work for the one with the square, the one with the repeated factor. So a works, c works, just not the one that doesn't have the square. Okay, because a is like the normal version that will work. Okay, so that is how carve-out rule works, and that's why carve-out rule doesn't work very 100% well for repeated factor. Okay, now there's a third case, right, and that is what we call the non-factorizable quadratic factor. Now, non-factorizable quadratic factor looks a bit like this, which is, well, you cannot factorize further, and therefore your partial fractions will be stuck with a denominator that looks a bit like this. Now, of course, we understand that if my denominator is x squared, which is non-factorizable, because if it's factorizable, you have to factorize. So it's non-factorizable, then therefore you end up with a fraction that with a denominator of x squared plus 1. The numerator is always 1 degree lower, alright? So it's what we call linear, bx plus c. And of course, you can imagine the carve-out rule will not work for b, will not work for c. Okay? It will still work for a, like the normal way as what we will do. So for example, in this particular question, right? If I want to find a, I just have to substitute x equal to 1. Okay? So x equal to 1, I'm going to get 1. This one, this is the part that we're going to cover, right? Because that's why we get an offensive number called denominator 0. So I'm going to put in the 1 here, all right? And you can see that a will be equal to half. Okay? So yes, the carve-out rule works for a because a is a linear factor that it looks pretty normal, right? It doesn't work for b and c. If you think about the reasoning, it's not that difficult because there is no value you can substitute in to make this into a 0. You can try, right? How to make this into 0? You can't. I mean, that's the whole idea of it being not factorizable, right? There's no way, okay? No way it can become 0. So you can put in x equal 1 to try, no, x equal minus 1 to try, this just doesn't work. So in other words, if you can't make this into 0, then you can't get rid of a. And if you can't get rid of a, you don't have the shortcut to help find b or c. So in that case, to find b and c, you have to go back to the basic steps again, which is to, well, multiply throughout by the common, the LCM of the denominators, and then, but the good news is, again, by carve-out rule, you already figure out a. So your job becomes a bit lesser, because now you're only left with finding b and c. Okay? So that's the quick rundown of what carve-out rule is, how it looks like when you do it properly, and how it works. Knowing how it works is important because your carve-out rule is not going to replace your original idea of partial fractions. Okay? So we come to the end of this short introduction to the carve-out rule. In a way, like hopefully you learn something useful that can help you. It's a shortcut, like I told you, okay, that you probably don't get to learn in school. Right, now if there's any more questions or particular topic that you want us to go through in this manner, please comment below and we'll see you soon.